Explainable AI, often shortened to XAI, refers to artificial intelligence systems designed to make their decisions clear and understandable to humans. Consider it as a bridge connecting the complex world of AI models with our human need for understanding. This ensures that AI remains reliable and accountable. Explainable AI is important because many industries require transparent decision-making processes. XAI helps organizations comply with regulations like the General Data Protection Regulation, which mandates explaining automated decisions affecting individuals. Understanding AI decisions builds user trust and confidence. When stakeholders can verify the reasoning behind AI outputs, they're more likely to adopt and rely on AI systems. There are mainly two types of AI explanations: model-centric and outcome-centric explanations. Model-centric explanations include feature importance rankings showing which inputs most influence the model's decisions, decision trees and rule lists that break down the model's logic into interpretable steps, surrogate models that approximate complex models with simpler, interpretable ones. Outcome-centric explanations include counterfactual explanations showing how different inputs would change the outcome, example-based explanations using similar cases from training data, natural language explanations describing the reasoning process in human terms. There are two types of interpretability: local and global. Local interpretability explains individual predictions or decisions made by the model for specific instances. It helps us understand why the model made a particular decision in a single case. For example, the LIME explanation for a single prediction will look like this. Prediction is assigned to model.predict applied on instance. Explanation is assigned to LIME explainer.explain instance. Instance is passed, then model.predict proba is passed. Global interpretability, on the other hand, provides an understanding of the model's behavior across all predictions. It shows overall patterns and feature importance that the model has learned from the training data. For example, a global feature importance will be something like this. Feature importance is assigned to permutation importance applied on model, x test, y test, and n repeats equals 10. LIME creates interpretable representations of complex models by approximating them locally with simpler models. It perturbs the input and sees how the predictions change to understand which features are most important for a specific prediction. For example, to use LIME for image classification, first import LIME image explainer from lime.limeimage, then assign LIME image explainer to explainer. Explanation is assigned to explainer.explain instance applied on image, classifier function, top labels equals 5, hide color equals 0, and number samples equals 1000. SHapley values provide a unified measure of feature importance based on game theory concepts. They show how each feature contributes to pushing the model output from the baseline to the actual prediction. To calculate SHapley values for model explanation, first import SHapley. Explainer is assigned to SHapley.tree explainer applied on model. SHapley values is assigned to explainer.SHapley values applied on X. To plot feature importance, apply SHapley.summary plot on SHapley values. X, plot type equals bar. Feature importance helps identify which inputs have the strongest influence on model predictions. This can be calculated using various methods including permutation importance and gradient-based attribution. To calculate feature importance, first import permutation importance from sklearn.inspection. Result is assigned to permutation importance applied on model, x test, y test, n repeats equals 10, random state equals 42. Then importances is assigned to result.importances mean. Counterfactual explanations show how input features would need to change to achieve a different prediction. They answer the question, what would need to be different to get a different outcome? For example, original prediction is that loan is denied. A counterfactual explanation could be, your loan would be approved if credit score increased by 50 points, monthly income increased by $1,000, debt-to-income ratio decreased by 5%. These explanations provide actionable insights that help users understand what changes would lead to their desired outcome. There are two types of visualization techniques. They are attention heat maps and feature attribution plots. Attention heat maps highlight which parts of the input the model focuses on when making decisions. Darker colors indicate higher attention weights. Feature attribution plots show how each feature contributes to the model's prediction using Shapley values or integrated gradients. Some of the best practices are: choose explanation methods appropriate for your audience and use case, combine multiple explanation techniques for comprehensive understanding, validate explanations against domain expert knowledge, document limitations and assumptions of explanation methods. Future developments include integration of causal reasoning with machine learning models to provide more meaningful explanations, development of interactive explanation interfaces that allow users to explore model behavior, standardization of explainable AI methods and metrics for better comparison and evaluation. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.